Probabilistic analysis and randomized algorithms are critical tools in computer science for addressing uncertainty in input data or algorithm behavior. This chapter begins by introducing these concepts and discussing their importance. Probabilistic analysis evaluates algorithm performance using probabilities, often to assess average case behavior. Randomized algorithms, on the other hand, incorporate randomness directly into their logic, providing flexibility in scenarios with incomplete input distribution knowledge. If you're unfamiliar with basic probability, it's recommended to refer to Appendix C, Sections C.1 through C.4, for a primer on probability concepts. These methods appear repeatedly across various computer science domains. For instance, probabilistic analysis aids in understanding how an algorithm might perform under typical conditions, especially when exact worst-case scenarios are rare. Randomized algorithms often solve complex problems efficiently by avoiding the pitfalls of deterministic approaches. Throughout this book, we'll revisit these methods and explore their applications, laying a foundation for designing robust and innovative algorithms. The hiring problem illustrates the practical use of probabilistic methods. Imagine needing an office assistant and relying on an employment agency to send candidates daily. Each candidate is interviewed, after which you decide whether to hire them. The hiring strategy is straightforward: replace the current assistant only if the new candidate is more qualified. This ensures you always have the best candidate so far, but comes with costs. Interviewing is relatively inexpensive, but hiring incurs a higher cost, including firing the current assistant. This scenario highlights a common computational challenge: estimating the cost of a strategy under uncertainty. In our analysis, we aim to determine the total hiring cost, balancing the trade-off between frequent candidate evaluations and minimizing unnecessary hires. This problem not only reflects real-world decision-making but also serves as a model for algorithms that must repeatedly evaluate and update optimal solutions from a sequence of data. The hire assistant procedure models the hiring problem using pseudocode. Starting with a placeholder dummy candidate, the algorithm iterates through all candidates, identifying the best one seen so far. Each candidate is compared against the current best, and if superior, they are hired. The cost model here focuses on interview costs C sub I and hiring costs C sub H, with the latter being significantly higher. This model diverges from typical algorithm analysis, which usually focuses on runtime. Instead, we count specific operations, interviews and hires. Regardless of the order, N candidates are always interviewed, incurring a fixed cost of O of C sub I times N. However, the hiring cost, O of C sub H times M, where M is the number of hires, depends on the candidate's order. This problem reflects real-world scenarios where maintaining an optimal winner from a sequence is key, whether hiring an employee or finding the maximum value in a dataset. Worst-case analysis of the hiring problem assumes candidates appear in strictly increasing order of quality. Under this scenario, every candidate is hired, resulting in N hires and a total cost of O of C sub H times N. This highlights the importance of evaluating average cases, as the worst-case scenario is rare in practice. The unpredictability of candidate order raises the need for probabilistic analysis. This approach provides insights into the average behavior of the algorithm by considering random input distributions. It allows us to estimate hiring costs under typical scenarios, enabling more realistic planning and strategy development. Probabilistic analysis involves leveraging probability theory to evaluate algorithm performance. It is commonly used to calculate the average case runtime or cost, considering assumptions about input distribution. For example, in the hiring problem, we assume candidates appear in random order, enabling a realistic cost estimate. However, care is needed when choosing input distributions. A poorly chosen assumption may lead to inaccurate results. When done correctly, probabilistic analysis not only aids in algorithm design but also provides valuable insights into problem structures, ensuring robust and efficient solutions. Randomized algorithms expand on probabilistic analysis by incorporating randomness directly into their processes. These algorithms rely on random number generators to make decisions, adding an element of unpredictability. A common assumption is access to a function random of a, b, which returns an integer between a and b inclusive, with each integer equally likely. For example, random of 1/10 may output any value from 1 to 10, each with a probability of 1/10. Randomized algorithms are especially useful in cases where input distributions are unknown or hard to model. They allow for flexible and efficient solutions to complex problems by shifting randomness into the algorithm itself rather than relying on assumptions about the data. The expected performance of such algorithms is evaluated over the random choices they make, often leading to robust average case performance across all inputs. Indicator random variables are a powerful tool for connecting probabilities and expectations in analysis. Defined as 1 or 0 based on the occurrence of an event, these variables simplify calculations involving repeated random trials. For example, let I of A equal 1 if event A occurs and 0 otherwise. The expected value of I of A equals the probability of A. Consider a simple scenario of flipping a coin. Let X sub H represent the indicator variable for the coin landing heads. Its expected value is 1/2, corresponding to the probability of a fair coin flip landing heads. Through the linearity of expectation, complex probabilistic scenarios involving multiple random events can be simplified into summations of these indicator variables, making them indispensable in algorithm analysis. The birthday paradox is a fascinating demonstration of probability. How many people must be in a room for the chance of two sharing a birthday to exceed 50%? Surprisingly, the answer is just 23, far fewer than the 365 days in a year. This result assumes birthdays are uniformly distributed and independent. To calculate this, consider the complementary probability that all birthdays are distinct. If k is the number of people, the probability that the first person's birthday does not overlap with the second is 364 over 365, the third is 363 over 365, and so on. The product of these probabilities gives the chance of no overlaps. Subtracting this from 1 gives the likelihood of at least one match. This paradox highlights the counterintuitive nature of probabilities in large combinations. The balls and bins problem explores how random distributions affect computational scenarios, such as hashing. Imagine tossing identical balls into B bins, each with an equal probability of 1 over B. Several questions arise. How many balls land in a specific bin? What is the average number of tosses until every bin contains at least one ball? On average, n over b balls land in a specific bin after n tosses. To ensure every bin has at least one ball, you need approximately b times lane b tosses. This is derived using geometric distributions for each stage of filling an empty bin and combining expectations. This problem, also known as the coupon collector's problem, illustrates how randomness affects distribution in computational tasks. Streaks in coin flips provide another interesting probabilistic challenge. If you flip a fair coin n times, what is the expected length of the longest streak of heads? The result is approximately theta of log n, derived through bounds on probabilities for streaks of varying lengths. For instance, the probability of achieving a streak of length k starting at a specific position is 1/2 raised to the power of k. Using this, the likelihood of observing a streak of at least 2 times log base 2 of n across all flips diminishes rapidly. Combining upper and lower bounds, the expected longest streak grows logarithmically with n. This analysis demonstrates how probability can bound expectations for complex random events. The online hiring problem introduces a new challenge: how to hire the best candidate without interviewing everyone. The key constraint is that after each interview, you must either hire or reject the candidate immediately, with no opportunity to revisit earlier decisions. To balance interviewing fewer candidates with maximizing the chance of hiring the best one, we adopt a strategy: reject the first k candidates, then hire the next candidate who surpasses all prior scores. This strategy ensures a systematic approach to decision making. The trade-off lies in determining the optimal value of k, which maximizes the probability of hiring the best candidate. The mathematical analysis of this problem reveals insights into balancing exploration, rejecting initial candidates, and exploitation, selecting from the remaining pool. The online maximum procedure implements the strategy for the online hiring problem. The algorithm begins by evaluating and rejecting the first k candidates while keeping track of the best score seen so far. From the k+1th candidate onward, the procedure hires the first candidate who surpasses this best score. If no such candidate appears, the last one is hired. The analysis focuses on calculating the probability of success, defined as hiring the best candidate. This involves determining the probability that the top candidate appears after position k and that no better candidate is skipped. By carefully analyzing this probability, we can identify the optimal value of k for maximizing success. The probability of successfully hiring the best candidate is given by summing probabilities over possible positions of the top candidate. For a candidate at position I, the probability is k divided by n times the quantity I minus 1. Integrating over all positions from k plus 1 to n provides a tight approximation for this success probability. Through analysis, we find that choosing k equals n divided by e, where e is approximately 2.718, maximizes the lower bound of the success probability. With this value of k, the probability of success is at least 1 over e, or approximately 37%. This result demonstrates the balance between interviewing enough candidates to establish a baseline and leaving enough room to select the best. Probabilistic counting methods, such as Morris's algorithm, demonstrate the power of probabilistic analysis in practical scenarios. In this approach, a counter can represent exponentially large values using limited memory. For example, a b-bit counter can represent values as large as 2 to the power of b using probabilistic increments. The increment operation adjusts the counter value based on probabilities, increasing the expected count while maintaining efficiency. After n increments, the expected counter value matches the true count, making this method a valuable tool for applications like database indexing or network traffic measurement where memory constraints are critical. Searching an unsorted array introduces various algorithmic strategies, each with unique trade-offs. Random search selects indices at random until the target value is found, while deterministic search iterates sequentially from the start. Scramble search permutes the array randomly and then performs a linear search. The expected runtime of each method varies depending on the input distribution and randomness. Randomized methods often excel in situations with limited prior knowledge of the data, providing robust average case performance. Comparing these algorithms highlights the importance of matching strategy to context for optimal results. In conclusion, probabilistic analysis and randomized algorithms offer essential tools for solving complex problems in computer science. These techniques enable us to design algorithms that are both efficient and robust, especially when faced with uncertainty or variability in input data. From the hiring problem to probabilistic counting, these methods demonstrate their versatility across diverse applications. By leveraging randomness and probability, we can derive innovative solutions to challenges that might otherwise be intractable. As we continue exploring these techniques, their role in advancing algorithmic design becomes increasingly evident.